from the grounding zone to the ice front in the Ross Embayment.
Thank you, Hugh, for a great introduction. And I know I'm standing between you and lunch. It's been about 5 hours we've been in this room, so I'll try and do this quickly. So I'm Matt. I'm at Colorado School of Mines. There's work that we're kind of just starting with Mike Dinneman at Old Dominion University and Wilson Sothoff, who's a PhD student in my group. And so this might not be the most satisfying talk because the project actually starts in 6 weeks. And so you're just seeing a little bit of a pilot study about what we're thinking about and where we're trying to go. Come back to a conference 3 years from now to see some actual results. Twitter handle if you want to, take a picture of me. Cool. So Hugh laid out a lot of motivation. I'm going to lay out a slightly different motivation, which is that our models of basal-melt and our observations of basal-melt don't agree. And Hugh actually showed some of Sushil's great basal-melt rates that he gets from altimetry. Here's just some integrated melt rates by draft for a couple ice shelves. In the pinks, you see, oh, the laser does work. In the pinks, you see the observations from Sushil, and then in the purple lines, you see a modeled freshwater flux from a coupled ice shelf ocean sea ice model. And you see in the shallow drafts, the model's performing pretty well, actually, I would say remarkably well. But as you get to deeper drafts, the models and the observations start to diverge. And Mike has thought for a long time, this is Mike Dinneman's model, has thought for a long time one of those key missing bits in here is the freshwater flux. We know from kind of past the ice shelf front that there are lots of things we can see that depend on freshwater processes in the subglacial environment, or in the sub-ice shelf environment, sorry. This is just one example from Pine Island Glacier because my group does some work on these polynyas, so I have nice figures. And so here the Pine Island polynyas just 1 year apart, and you can see there's a huge variability. And to create one of these sensible heat polynyas, you need some buoyancy, and that can come from freshwater flux from the ice shelf or freshwater flux from the grounded continent. If you look over a longer time series, there's some work we have in review right now. There is a huge amount of variability of these polynyas. Now we're talking about variability in CO2 fluxes, nutrient fluxes, things like that. So freshwater matters a lot, and we're not quite capturing the freshwater dynamics in these sub-ice shelf cavities yet. And we think that this source from the continent is one of those big drivers that we're missing currently. And in particular, we're interested in the time variability of that, maybe just because I study these subglacial lake outbursts, or because the time variability matters. I don't know. We can discuss that over lunch. When we think about time variability of the subglacial water systems beneath Antarctica, you always need to remember this is not surface water like you would get in Greenland and mountain glaciers, and there are no real projections that say that's going to change anytime soon. And so you really need to peel the ice away and think about the processes going on at the ice bed interface. That's the only place we're creating water here. And if we're truly interested in the time variability, we're interested in these interconnected lakes down near the fringes that modulate the flow of water downstream. And so the water's being generated mostly in the upper catchment, and then it flows through these systems, kind of gets hung up in these subglacial lakes that then can fill and drain and release water downstream. Here's how we actually identify these subglacial lakes. As Hugh said, it's really hard to actually capture these freshwater fluxes from observations, and so we look at altimetry measurements. And so there's an example from ISAT-2 altimetry from the past couple of years. This was published 2 years ago now. And you're seeing 3 months of data posted every month, so a moving time window of surface heights. And we're seeing the surface heights go up and down in these confined areas. And from these surface observations, the ice sheet surface, we're inferring that there's a water column at the ice bed interface that's thickening and thinning through time. So water flows into the lake, it jacks the entire ice column up, we see that on the surface. And these can be very large. And so there's just this question about Yokalups. Well, here's an event in the Slessor catchment feeding the Filchner Trough, where we think we have about 2.5 cubic kilometers of freshwater coming out in about 9 months. If you look at the peak freshwater flux coming out, it's about the Colorado River going through the Grand Canyon this time of year. And that's a lot of water. And you can imagine it's going to be hard to kind of understand these sub-ice shelf cavities if you don't understand the freshwater dynamics coming in. And so that really drove this question of ours: what's the impact of this time and space varying freshwater input from the continent? And that's going to require 2 steps. The first is actually trying to estimate this time-varying input of freshwater, and we're going to do that through satellite altimetry, and then use that satellite altimetry information, route it downstream, and use that as a river input into a coupled ice shelf ocean sea ice model. And then we get to see what it does. Just want to note, we're not the first people to come up with this idea. This was first estimated, particularly the time and space varying aspect, the observationally driven part of this, was first estimated with ICESat data, which was a laser altimetry mission from 2003 to 2009. The problem with it is it's not continuous data. It was episodic, collecting data 2 or 3 times per year. So we don't have this beautiful little time series that modelers are going to want. But just this study shows you in these pictures, the details don't matter, but the colors are the water flux relative to a control study. And so if you have these subglacial lakes, how much does that impact the subglacial water fluxes? You see reds and blues, okay, these subglacial lakes matter. And so we started to dive into the altimetry data. This is the work that Wilson is doing. And as soon as you start opening up this newer generation of altimetry data, you first realize there are probably a lot more lakes that we haven't noticed. And then also that these lakes are not these nice little features that just sit there, but they grow and shrink over very rapid timescales sometimes. And so the altimetry part of this was a little bit more involved than we had hoped, and so we're working through this right now. And here are just some examples of kind of lakes we didn't know about, outlines changing dramatically. All of this can bias the freshwater fluxes that we're coming up to, and so this takes a careful eye, and that's what Wilson is working on. One of the really great parts of this is the density, the spatial density of this data from CryoSat-2 and ICESat-2, just 2 altimetry missions, really allows us to be confident in where we think this water is coming out. We're still doing kind of probabilistic estimates of where this is coming out because all of the grids we have are not well constrained, but at least we can constrain it a little bit more. On to the models, which is the more exciting part. We developed a pilot study where we used that old ICESat estimate, in particular where that water is coming out. So it looks like there are about 6 locations over the West Antarctic coast of the Ross Ice Shelf where fresh water can come out. And so what happens if instead of taking fresh water and just putting it into the ice shelf cavity from the entire grounding line, but just using 6 places and kind of thinking about background flow? And so on the left, we have a base case with no subglacial discharge. These are ice shelf basal melt rates coming out of the ROMS model. And then here's where you take just 6 locations. You can kind of see where the hotspots of melt are. So those are the locations, and we just start dumping some background flux into the model. The people in the back are probably like, well, those look pretty much the same. And so we look at a melt rate difference, so an anomaly map basically. And you can see over most of the ice shelf, it does look the same, except we do get these hot spots of melt right at the grounding line, which you would, of course, expect as you put that freshwater buoyancy into the cavity. But you also get far field impacts, too. And you see you have this kind of subglacial freshwater flow line going on, increasing the basal melt rates, particularly hugging in ice rise right there, a pinning point, which is really exciting to me as a glaciologist, because it means unless we have the freshwater fluxes right, we're not going to get pinning point evolution and buttressing right as you start to project these into the future. Our next experiment in this pilot study was looking at time-varying outflows, so just basically turning these outflow points on and off. And what you see is, again, they look pretty similar, but the magnitudes actually just increase, both negative and positive. Blues get bluer, reds get redder. And so that's actually particularly true in the far field, if you look up here at the front, for example. And so the time-varying aspect, interestingly enough, I didn't expect that, that the time-varying part of this really impacts the far field a lot more than the near field. We're also thinking about biogeochemistry and how this impacts past the ice front. And so we're putting some iron tracers into the model. This is the upper 10 meters of the water column, either below an ice shelf or below the surface when you get outside of the ice shelf cavity. Just the upper 10 meter mean of dissolved iron. We're injecting the tracer based on the subglacial lake dissolved iron concentration, which we have taken a sample of 2 lakes. So whether or not this is representative is a whole nother argument we can get into. So there are a lot of caveats here. But we get these high concentrations that you would expect right at the input locations. But this all does travel downstream and ultimately out into the open ocean. And out into the open ocean, in pretty high concentrations, high enough that we overcome the iron limitation threshold that we usually think about. And so now we're starting to think about how the continental freshwater systems are impacting the open ocean biogeochemistry. Moving forward, we're going to start to develop some high-resolution models in the Weddell and the Amundsen. We're also starting to think about freshwater connectivity, so we're going to use a circumantarctic model for that, because what happens in one shelf doesn't stay in one shelf, as I just showed on the previous slide. Quick summary, I'm being kicked off the stage, and we all want to eat lunch. And so here's a little drone view of the camp that gave us this beautiful dissolved iron concentration that we're using, some nice eye candy before lunch. Thank you.
Thank you, Matthew, for wrapping up a session. One very quick question, otherwise discussing over lunch. There's one over there.
Hi, Matt. I had a question about the hot spots you mentioned upstream of Roosevelt. Might it be coming from that adjacent coastline?
So we don't
toward the east.
We don't have any connectivity in that model. This model only has the Ross Ice Shelf inputs of freshwater. So that's why we really need to expand it to a circumantarctic model.
Okay. Don't forget to check out the posters related to today, including mine. And there are a couple of announcements that are to be made.
Yes, I just